Okay, so let me demonstrate for you something about what we call the coefficient of friction. If I place this block on an incline, so you probably know about the different forces that are acting on it right now. Gravity, of course, pulls straight down. And then the normal force, which is a way of saying the ramp pushes up on the desk, actually doesn't push straight up, it pushes up and out, right? The reason we call it normal force is in the mathematical sense of normal, that push from the surface onto the block is perpendicular to the incline. So normal force this way, gravity this way, and we break that force of gravity into two components. There's a component of gravity exactly opposite that normal force, and there's another component of gravity pointing down the incline. And as the ramp gets steeper and steeper and steeper, the component parallel to the incline gets larger, which is exactly the nature of the sine of theta, right? For very small angles, the sine of theta calculates as a low value, and for very large angle, it calculates as a large value. So it should make sense that the component of the weight vector down the incline is described as mg sine theta, and therefore at low angles, there's a small component this way, and at great angles, there's a large component this way. And exactly the opposite happens for this component of gravity, right? True gravity is straight down, but there's a perpendicular component to gravity. And when the angle of the ramp is very low, that component of gravity should be large. And when the angle is very steep, that component should be small, which is exactly what happens when you calculate the cosine of theta. So it's pretty easy to remember that parallel to the incline is mg sine theta, perpendicular to the incline is mg cosine theta. This way is the normal force, but clearly we have an object in static equilibrium. Must be another force this way to cancel out the component of gravity this way, and we all know that that's friction. So friction is a force that depends on the strength of the normal force. For example, if I lift the incline this high and it starts to slide, how could I stop it from sliding at this incline? Well, I could take my finger and push like this. Essentially what I'm doing is increasing the amount of contact between the two surfaces. So the point is that as the normal force gets greater, right, as the force of contact this way onto the block becomes bigger, so does the frictional force this way. Another way in which the frictional force can become greater is by changing the surfaces. So this is felt on metal, but maybe rubber on metal is grippier, or stickier, or rougher, however you want to say it. So there's really two things that factor into this force of friction. There's the coefficient of friction, which is a description of which materials are in contact. It's just a way of saying how smooth or how rough. And then there's also the normal force itself. When we multiply coefficient of friction times normal force, we get friction force. Well, there's two different coefficients of friction. There's the coefficient of friction that's involved in keeping it at rest, and there's a different coefficient of friction involved when it's sliding. And we can determine the values of those coefficients with a simple experiment. We raise the incline until we find the maximum angle at which it no longer stays at rest. And it's a simple matter of using maybe an inclinometer and putting it on the incline to measure the angle, and then grabbing a calculator and taking the tangent of that angle, and that'll give us the value of the coefficient of friction. So let's see if we can figure out how steep does this have to be before it starts to slide. Now, did you see that? I'm going to back the angle down one more time. Put this on here, kind of like you might walk when you step on an incline, you really set your foot and twist it in good. We can establish something known as frictional welding. Okay, here's what I want you to see, that once I get the angle steep enough that that frictional welding breaks and the materials start to just slide across each other, that it doesn't just move at a steady speed. If I break the frictional welding and overcome the maximum static friction, that the object actually accelerates. Let's find out. Am I lying when I say that? What's the maximum angle I can get it to before I break frictional welding? There it is. The motion down the incline is not constant velocity, it's constant acceleration. So here's another experiment I can do. Now that I've found the maximum angle at which it'll stay at rest, I back the angle down a little bit, make it not so steep, and give it a little push, and see if it accelerates or moves with constant velocity. It looks like it's accelerating even at this incline. So I back the angle down a little more still, give it a little push. That looks about like constant velocity. So you see the maximum angle that it can reach and stay at rest is a greater angle than the angle that I reduce it down to, such that its motion is constant velocity once you give it an initial push. So now I measure that lower angle, take the tangent of that, and I've just calculated the coefficient of kinetic friction. So the coefficient of static friction is always greater than the coefficient of kinetic friction, and we see that because the maximum angle that you can create in the incline and have the object stay at rest is steeper than the angle at which it'll slide at constant velocity.